So, warm up today. Talks about a pendulum swinging. It says the first swing of a pendulum travels 40 centimeters. Each subsequent swing travels 95% as far as the previous swing. And then there are various questions that follow that. Now, starting off just looking at that first piece. Tells us the first swing of the pendulum is 40 centimeters. John, what's that telling me? A sub 1 is equal to 40. Each subsequent swing is 95% as far as the previous. Lauren, what's that telling us?
That is R.
It is R. Now, is it directly R or is it a modified R? This one is directly that, because 95% as far as the previous one is 95% of the previous one. So that is telling us R directly. It's a modified version if it talks about increasing by 95% or decreasing by 95%. Those you have to either add 100 or subtract from 100. This one just is 95% as far, so that is exactly R. Okay, except there is, you're right, one modification. I don't put 95. I put 0.95. Okay, find the distance traveled in the 30th swing. Bryn, 30th swing, what's that telling me? N is 30 for this first problem anyway. Now we've got R, so it has to be geometric. Leaf, if I'm talking about the 30th swing, am I talking about a sequence or a series? Specifically the 30th swing, a singular swing is a sequence thing. So this one's a sequence. Most of them are series. This one happens to be a sequence. So geometric sequence, A sub n equals A sub 1 times R to the power of n minus 1 is the formula for a geometric sequence. So A sub n or A sub 30, I can write that. I can stick with A sub n. You've probably noticed lately I don't change the subscript as much. 40 times R is 0.95 to the power of 30 minus 1. Now, before I type it in, I'll probably simplify that piece. On the 30th swing, the distance it travels, I'm going to go with 2 decimal places, 0.4. What unit would go on this? Because this is a word problem. Centimeters. Next question asks about the total distance traveled. Elsa, what's the change when it says total now instead of the specific 30th swing? Now we're talking about the series. Okay, got a couple of formulas for this. The one that makes sense is the one that uses A sub 1, R, and N on this one. Could I use the one that involves A sub N? Yeah, I found it, but I had to round it to get there. So this formula goes, oops, I started writing the other one anyway. Let's try this again. A sub 1, 1 minus R to the power of N over 1 minus R. So, A sub 1 we said was 40. Parentheses, 1 minus R, 0.95 to the power of N, which is 30, all over 1 minus 0.95. Brooke, in order to type that into my calculator, what do I need to add to this before I type it in? Where? Around that denominator, around the bottom of that fraction, exactly. Okay, so 41 minus 0.95 to the power of 30 divided by 1 minus 0.95 in parentheses. I get 628.29? Again, what's the unit on this one? Still centimeters. In fact, they would each be centimeters. Next question asks about what about the 100th swing? Now this is still referencing a total, so it's still referencing a series. Shelby, what's the change in this one? What did they change to go from this question to this question? N. N is now 100. So my formula looks very, very similar. 41 minus 0.95 to the power of 100 this time over 1 minus 0.95. And just like we did before, we're going to put parentheses here. Now, did y'all know about your calculator's ability to just put in the last thing you typed in without having to mess with all the stuff? Works on both Casios and TIs. It works in a slightly different way. Now the Casio, I didn't have anything typed in, so let's get that in there real quick. Oops. And I'm just going to type in, oops, I meant to type in the previous one. Okay, on your Casios, if you want to change something in there, if you accidentally type something wrong, or in this case, we want to change the 30 to 100, you scroll up and click the left arrows, and you should be able to change that to 100. In the TIs, it's a little bit more challenging, but it's nothing too terrible. Do you see where it says entry right above your enter key? If you hit second, and then the enter button, it'll bring you the last thing you typed in. Now, the only problem is on the TIs, they default to writing over the top of what you have. So putting a 100 in a place of a 30 is not the easiest. I can replace the 3 with a 1, but then if I click second and the delete button, it'll change my cursor to insert things. So now I can type a bunch of things and it'll add it to the equation. The moment you use your arrows to move, though, that goes away. Either way, you could just type it in again, but if you didn't want to, especially if it's a long equation where you just have to change little things, that can be helpful. I get 795.26. Again, it's a word problem, so centimeters. What about the 150th swing? Faith, what changed? N becomes 150 now. So, go to my calculator. I'm going to be lazy and not write out the equation again this time because I know that the change is going to be this. I get 799.64 centimeters. Okay, next one says, what about the 200th swing? Jaden, what's the change?
You switched the 150 to 200?
Mm-hmm. N is now 200. Okay, so second, enter. Scrolly, scrolly, scrolly. Change that to a 200. Now I've got 799.97. What if we continue this pattern forever? How far do you think that that pendulum will swing?
It would become an infinitely long decimal.
Become an infinitely long decimal. Okay. Other thoughts?
It would stay around 800.
What was that?
It would stay around 800.
Stay around 800? Because do you notice that it's, at first, when I look at the series, we notice big leaps, but then the leaps get smaller and smaller. So staying an infinitely long decimal, technically true. Getting closer to 800, also technically true. In fact, let's change this to 300. Let's change it to 400. Let's change it to 500. change it to a significantly larger number that I don't know how many zeros I typed in. What distance do you think it'll travel? Well, if we explore a little bit in our calculator, the answer is 800 centimeters. Why is it, do you think, that I could continuously add numbers, but it stops getting bigger? They would cancel each other out if they were positive and negative, but every single one of our 95% of the previous terms is still a positive number, so nothing's canceling out. Let's look a little bit closer at the individual swings. So let's talk about the sequence aspect of things, except instead of on the 30th swing, let's talk about the 100th swing, for example. That's how far the pendulum is traveling on the 100th swing, about 1/4 of a centimeter. Tiny little amount. Okay, what about that 150th swing that we talked about earlier? About 100th, about 200ths of a centimeter. The 200th swing. About 1,000th. What are you thinking? It'll stop moving in the sense of reality, and eventually in real life things have to eventually stop swinging. That is true. In the sense of mathematically it never actually stops, but it starts moving such a tiny, tiny, tiny amount that we don't notice it. Because right now, these are scientific notation. This one's got 7 zeros in between the decimal point and the 5. Eleven zeros between the decimal point and the 1 here. So it doesn't stop moving completely, but the amount that it moves becomes so obnoxiously small that essentially it's as if it stops moving. And eventually our calculator can no longer understand how small it is moving, and it does tell you that it stops. Now, this leads us into section 10.4, which is talking about infinite series. We've mentioned before that when it came to the series that we were talking about in this class, that we had been talking about a partial sum. And a partial sum is the sum of part of a sequence. And I haven't actually defined that. I've mentioned it many times, but I haven't actually written it out. Versus now, we can have infinite sums or infinite series, which is the sum of an entire sequence. Now, when we're talking about finding the sum of an entire sequence, in all actuality, we are eventually working with this situation where we're adding numbers and they end up making such a minute change that that's why eventually we're able to say, it hasn't changed anymore. Now, in doing this, we're technically talking about a sequence doing something known as converge. or it can be convergent. To converge means to essentially get closer and closer and closer and closer and closer to something without technically actually hitting it. It's that idea of working with essentially an asymptote. Graphs converge to the asymptotes. An infinite sum converges or is convergent if it has an actual sum. Has a specific sum. It's this idea a series approaches one number. And that number we say is the sum. We say is what it converges to. Now, if it can converge, it can also do the opposite of converge, which is to diverge. A series diverges if the infinite series has what we say is no sum. Or more specifically, the series approaches a positive or a negative infinity. It just keeps getting bigger and bigger and bigger, or smaller and smaller and smaller. So, first we are going to talk about the infinite arithmetic series. We're going to explore a little bit in order to find the sum of these, because we have enough information to find the sum of both arithmetic and geometric series. We're going to start with the series 5, 7, 9, 11. It is arithmetic because in between terms it is adding 2. Now, to explore this a little bit, we're going to do a little bit of good old-fashioned adding. So, as I start adding terms in this sequence, upon initial inspection, it doesn't appear to be going to anything. I can also approach this using my arithmetic series formula. Using my arithmetic series formula, I can just start making n bigger and bigger and bigger and see what the pattern holds. Say I add up the first 1,000 numbers. It'd be 1,000 divided by 2. 2 times the first number in this sequence was 5, plus we're adding up 1,000 terms minus 1, and every single term increased by 2. And I get a really big number. So that's the first 1,000 numbers added up. Okay, I'm looking for a pattern here. Let's try adding 5,000 numbers. 8,000 numbers. 10,000 numbers. Does it appear to be leveling out at anything, kind of like our warm-up one did? No. Does it make sense that it wouldn't level out? Aren't we just adding increasingly big numbers? Is it ever going to stop getting bigger if I'm just adding bigger numbers? No. So, this arithmetic series diverges. And it diverges because of the fact that as I'm adding 11 and then 13 and then 15 and then 17 and then 19 and 21 and 23, those numbers I'm adding on are just getting bigger and bigger and bigger. And I can't add bigger and bigger and bigger numbers without expecting that the series is just going to get bigger and bigger and bigger. So what are some alternatives that I can do to a arithmetic series that might make it where it doesn't do that? Well, I can't keep adding bigger and bigger and bigger, so maybe start adding the opposite, smaller and smaller and smaller. So I can start with something like 12 and 9 and 6 and 3, and now the numbers are getting smaller. And if I do this, let's say I add up 1,000 of these. A sub 1 is now 12. I'm adding up 1,000. The difference here is a -3. And if I do this, add up 5,000, add up 9,000. Same problem. Now they're just getting infinitely smaller. It's going towards negative infinity. It also diverges. In fact, every single arithmetic series is going to be divergent. So, you'll probably noticed that I didn't write a title on here. I did that on purpose because today's section is called Infinite Geometric Series. Because we don't really need to explore the arithmetic series, because arithmetic series, the infinite sum is always going to be either infinity or negative infinity, and therefore it will diverge or be divergent. Okay, so let's talk about geometric. Now, when it comes to working with infinite geometric series, we will find that some of these do converge, not all of them. In order for a series to converge, what has to happen is the number that I'm adding on has to get not just smaller and smaller and smaller, but closer and closer to the number that when you add it, it doesn't make a difference. What number do you add and nothing happens? 0. It has to get closer and closer to 0, which means when I'm going from term to term and I'm multiplying by something, the number that I multiply by has to get the number closer and closer to that 0 number. What do you multiply by that gets something closer and closer to 0?
Anything between 0 and 1.
It's part of it. Anything between 0 and 1? Or 0 and -1. The negative side of things too. So infinite geometric series. They will converge if and only if the absolute value of the constant ratio is smaller than 1. If the constant ratio is 1, it will not converge. If it's -1, it will not converge. If it's bigger than 1 or smaller than -1, it will not converge. In those cases, it will diverge. Now, the sum of the series itself. First off, the sum of an infinite series. We'll start off with not s sub n, but s sub infinity, because we're adding up an infinite number of terms. Now, it is a modified version of our geometric series formula. It's a modified version of this specific one. Now, what ends up happening is that r piece, as we continue to multiply by it, it gets closer and closer and closer and closer to 0. Now, the continued multiplication piece of this formula, continuous multiplication is exponents. So this piece right here, this r to the power of n, is what gets closer and closer and closer to 0. Now, if that becomes a 0, these parentheses become 1 minus 0. What is 1 minus 0? 1, right? And a sub 1 times 1 is just a sub 1. The formula for an infinite geometric series is a sub 1 over 1 minus r. Assuming that r in absolute value is less than 1. In other words, assuming that r is between -1 and 1, not including either of those specific values. If that is not true, the formula will get you a number, but it will not be accurate. So you do have to check r. So now you're going to start seeing things where it asks you to find the sum if it exists. It's not going to always exist. You're going to have to pay attention to the problem. Now, when it comes to these infinite series, they're not necessarily going to tell you it's an infinite series. How you're going to know it's an infinite series is they don't tell you in any way where to stop. They don't tell you that n is a specific value. Or they do not tell you we're going to add up 54, 36, 24, blah, 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 and then stop at, I don't know, another number in the list. But if they have an end value, if they have the ... plus a number and then the ... stop, that's not infinite. The other way you could tell it's infinite is they'll ask for s sub infinity. If there's an infinity in the problem anywhere, it's an infinite series. Okay, now in this case, it's just the ... goes on forever. In order to determine if you can find the sum of the series, the first thing you need to do is recognize, is it geometric? 54 to 36 to 24? Definitely not arithmetic, but does that make it geometric?
Yes.
It doesn't make it geometric, but this one is geometric. Remember, geometric, you're multiplying by the same number to get from term to term. If you can't obviously see what you're multiplying by, work backwards. The opposite of to multiply from left to right is to divide from right to left. Take a term, divide it by the term before it. Change that into a fraction. According to this is times 2/3. Yup. And the pattern holds. So, it is geometric. It is a series because I'm looking for a sum, and it is infinite because there's nothing indicating where to stop. R is 2/3. Now, the moment that it's an infinite geometric series, you need to double check if R is in the correct range. R needs to be between -1 and 1. It's 2/3 between -1 and 1. Yes. So it does converge, and therefore you can find the sum of the series. To find the sum of the series, S of infinity equals A sub 1. What's A sub 1? 54. Over 1 minus R. We already established R was 2/3. Now before I go typing that into my calculator, what do I need to add? Parentheses around the denominator. S of infinity is what? 162. Okay, got just a couple more examples for you. Two plus 5 plus 12.5 plus ... Is it arithmetic or geometric? Definitely not arithmetic. Could be geometric. Take terms, divide them. 5 divided by 2, well, is 2.5, which I can leave as 2.5, or I can write as 5 halves. So it is geometric. I know it's infinite because it's going on forever. It doesn't tell me where to stop. It is a series because I'm asking to add it. Before I type into the formula, what do I need to check? R needs to be between -1 and 1. Is it? No. In fact, you didn't have to calculate R to know that. If R is between -1 and 1, the numbers are going to get closer and closer to 0. To go from 2 to 5, are you getting closer to 0? No, the numbers are getting bigger. It diverges. There is no sum. They might ask you to find S of infinity. Another indication they're looking at an infinite series. It's infinite. We need it to be geometric. Is it? Yes. What are we multiplying by? It's divided by half, so we're dividing by 2. We're multiplying by a -1/2. Or you can write that as -0.5. That's fine. Will this one converge? Is R between -1 and 1, in other words? Yes. So it will converge. Therefore, I can plug into my formula. My formula says S sub infinity is equal to A sub 1 over 1 minus R. A sub 1 is 12. R is negative 1/2. S sub infinity equals 12 over 1 minus negative 1/2. Before you type it into your calculator, make sure you're putting parentheses around that denominator. 12 divided by 1 minus a negative 1/2 is? Eight. When R is negative, you'll find that the sum doesn't tend to be a giant number. Okay. I've got one more problem. Something that you're going to see and you're going to have to pay attention to. And that's this. With an infinite series, they can do sigma notation the exact same way that we can for a non-infinite series. What tells you this one's infinite? There's an infinity symbol. We're adding up an infinite number of terms. Is it geometric or arithmetic? It's geometric. You can tell that because exponential form. The variable is in the exponent. If it's not in the exponent, it's arithmetic. Arithmetic infinite series are divergent. So this is an infinite geometric series. We know it's a series because it's sigma notation. How do we find a sub 1 when it's in sigma notation? Take that number and plug it into the expression. 18 times negative 4 fifths to the power of 1 minus 1. Now, for some reason, that 1 minus 1 exponent messes with people. Being to the power of 0 does not mean it becomes 0. Anything to the power of 0 is 1. That doesn't mean the entire first term is 1, though, either. The negative 4 fifths to the power becomes the 1. It becomes 18 times 1, which is just 18. When in doubt, type it into your calculator. What's R? Negative 4 fifths. The base of the exponent is R. Now, if R is negative 4 fifths, does it converge or diverge? Converge. That's between negative 1 and 1. S sub infinity is 18 over 1 minus a negative 4 fifths. Don't forget the parentheses. The sum of this infinite series is 10. Infinite geometric series. Nothing too terrible? Make sure that you are adding this formula to your formula page. I'm adding that there's that caveat that the absolute value of R must be less than 1. Now, keep in mind, I talked to you guys a little bit. I showed you what the last page of your quiz is going to look like tomorrow. I mentioned that you're going to have to tell the difference between which formula. I'm going to tell you right now. Formula's on there, but it doesn't mention anything about R. You need to know that piece.